As you may realize, I'm not talking about a specific Google technology. I'm talking about abstraction. Abstraction is important to Google, but it's important to every engineer, every designer, every developer, no matter what technologies they use, and I'll try to show that. The title, besides, of course, mimicking Pirsig's famous Zen and the Art of Motorcycle Maintenance, is intended to suggest an approach to abstraction that is not passive and receptive, but active and involved. Nevertheless, I'm not talking to past masters of the art of design, development, maintenance. I'm trying to address a crowd that's middling to low in terms of having reflected and worked on these issues. So if this talk proves boring because you're way past anything I explained, I apologize, but don't say I didn't warn you, although the warning came just now. So the motivation to talk about abstraction is that our life, our professional life, lives on a tall tower of abstraction. Suppose you're programming in assembly language, as the upper right of this broken tower appears to suggest. You may think, well, I'm being as concrete as one possibly can. Hey, I'm programming in assembly language. Very few people do nowadays. Well, assembly language is an abstraction for machine language, the hexadecimal number right below it. Machine language, in turn, is an abstraction of the internal working of a machine with memory, an ALU, control units, and so on and so forth. And all of these concepts, what's an ALU, what's a RAM chip, are abstractions of a bunch of transistors in various configurations. A transistor, in turn, is an abstraction of actual deposition of silicon and dopants on a flat chip, and so on down to, I stopped with Schrödinger's equation, but I suspect a physicist, I'm an engineer, not a physicist, could explain to me how Schrödinger's equation is a simplifying abstraction of something much more complicated on the way down. So even when we're looking at the very lowest layers of software, we are already standing on top of a fragile and tottering tower of abstractions. Why do we do that? Why don't we just reach for the Schrödinger's equation and manipulate them directly to do our bidding? Because it's a lot of work. We need some leverage. Abstraction is leverage. Like Archimedes say, give me a point of rest, a fulcrum, and I can move the world because of the lever principle. Levering up lets me do so much more. However, if I'm not careful and I don't understand how much the leverage amplifies my good thing and my mistakes, the whole thing can come crashing down on it. Which is why I think it's occasionally not a bad idea to think about what it is we're doing and how to avoid leverage crashing us into disaster. Abstractions. We can't live without it. All knowledge work, programming is my field, but it applies to lawyers, it applies to doctors, it applies to user interface designers and industrial designers. Knowledge work is work that uses abstraction layers produced by others and produces new layers on top, enabling others to perform tasks well beyond their normal levels. Can we live with this frightening power that abstractions provide us, and that the abstraction we design provide others in turn. We can, as long as we realize and control the fact that whole abstractions leak. Like this kid trying to stop it up. All abstractions leak. This is called Spolsky's law because it was first formulated and published by a well-known blogger, book author, and founder of Stack Overflow, Joel Spolsky. There are several attacks deliberate by nasty guys trying to breach the security of the abstraction, and also perfectly accidental bugs, overloads. The fact that attacks by nasty guys are the least of our worries is suggested to me by one of my legendary colleagues at Google. I think he's employee number 19, I believe. I was once discussing with him and a security expert what hiring conditions should we have for a security expert, and the security expert claimed, well, the point number one of a really good security expert is that he's a paranoid. He always sees attacks coming from everywhere. And my friend, the founder of the reliability engineers at Google, said, yeah, right. I know you security guys. You claim you're paranoid because you think all human beings are about to attack you. That's nothing. The whole universe is attacking you all the time. You only think about evil human beings. You're totally optimistic. I mean, an asteroid is probably crashing down toward a data center. Are we prepared to? It's not directed by an evil genius master. It's just the way the universe is always attacking us. So that applies to the attacks against abstractions as well. To understand this, my core contention in this talk is that to really be great at one level of abstraction, you must understand, you must grok, you must get a few layers below the level you're working at. If you only understand the world from a certain level of abstraction up, you're not the best you can be at that level. In addition, and this is my own personal thesis, don't want to taint Mr. Spolsky with it, I believe abstractions should leak. Leak in well-designed, architected ways on appropriate occasions. I'll show some examples. Also, never forget that good as abstraction may be, it can slow you down. The equivalent is, okay, so I have this lever, I can move with my limited force a huge boulder. Yes, but I'm going to have to move my arm 2 meters to move that boulder 2 millimeters. So it will move very slowly. That's just about as far as the parallel can go. But I'm probably not thinking of the same thing you are when I say abstraction can slow you down. You're probably thinking, oh, well, yes, if I program in Python, a high abstraction layer language, that will be slower than programming in machine code. That's nothing. That doesn't matter. The point is abstraction slows down your human responses. Believe it or not, there's peer-reviewed results in the psychological science literature. I'm giving the complete reference, so please, by all means, go and read this excellent article. To abstract is to procrastinate in our minds, in our psychologies. Specifically, by abstraction, the term these highly sophisticated specialists use for abstraction is construal level. An event that's remote is mentally constructed at higher abstraction level than one that is near, about to happen. So think of the dinner you had yesterday now. That's a pretty close event, and you probably have a pretty concrete memory of the food you had, whether you enjoyed it, if it was a venue, how was the service. It's rather specific. Now think about the dinner you had a year ago, unless that happened to be an incredibly exceptional day for you and stands out in your memory. Your memories are going to be extremely abstract because you can't afford to have very specific, precise, concrete memories of every dinner in your life. There's just too many. So the nearby ones, you have pretty concrete memories. The further away you move, the least precise your, so the least detailed, the least concrete, the more abstract is the mental level at which you construct. This is a pretty obvious result, but what wasn't obvious until these guys did their research and published it, is that when you construe something at a high abstraction level, when you conceive, for example, of a task as something in a pretty abstract way, you're far more likely to procrastinate. That is, not start doing it right now, but thinking, well, tomorrow sounds good, or maybe Monday. Of course, all the experiments, like everything in the literature about psychology, behavioral economics, all sort of related fields, the subjects are always students of psychology because that's a kind of experimental subjects that their professor can have for free. So we think we have a pretty good knowledge of human psychology. What we're pretty sure, we have a great knowledge of the psychology of undergrad students in psychology. So let's hope it generalizes, but that's a side note. So if to think in abstract terms fuels your natural propension to procrastinate, don't do it yet, it stands to reason that the reverse applies. If you want to achieve something, think in very concrete terms. I'm not the inventor of this. I just see it as the flip side of the abstraction leads to procrastination concept there. Probably the best known and still well worth reading book, been around for years, but human psychology hasn't changed in the last few years, is Allen's book, Getting Things Done. It's actually a sort of a cult movement. The focus is on a simple plan that leads you to think at any time about your single next action, the single thing you're going to do right now. Very concrete thinking leads to no procrastination. Of course, it better be the right thing as opposed to something you could, that was absolutely no hurry, and is not going to take you any closer to your goals. But you should read the book to find out how exactly you pick that one next concrete action that you're going to do right now. Another example, interaction design, user-centric design. The experts, user experience designers and so on, hardly ever say the word the user. What they do is they design personas, like John or Mark. They give those personas some character. They make concrete what are fictitious in a sense, but representative. So I'm designing this particular system for John, who is a young newbie trader with vast video game experience, or rather, I'm designing it for Mark, who's been trading since the time of King Hammurabi of Babylonia, and is using a computer this day that thinks it's not quite as handy as the clay tablet and the cuneiform character that he was used to. Of course, the way you design a user interface, a flow of user experience, is going to be different if you're targeting Mark or if you're targeting John with his instant reflexes, fast action, and so on. But the point is, they're both so much more profuse to design for than this vague user. And similarly, instead of describing the tasks that your software system is going to, or system more generally, is going to help the user do, you're going to design concrete scenarios. John just found out that a coup in Madagascar is going to stop the mine that he was investing in and desperately needs to hedge against. You see, you design a hypothetical, concrete scenario with a somewhat fleshed out persona at the core, having to deal with concrete circumstances in a hurry. You design to make that kind of task as easy as they can be. You think concrete, even in this case fictitious, because you don't really know if John is going to buy your system, but just in case, that's who you're serving. Jason Fried, the founder of 37 Signals, one of the great places to go for user experience design and expertise, puts it in a very simple way. Prefer action to abstraction. He's seriously convinced that the reason most user interface, user experience flows are really poor is that their designers were thinking too abstractly. And they should just start doing things and trying them out in the real world instead. Action, not abstraction. Once you have a clear picture of the cost, potential cost to you, of abstraction, you can start using it more deliberately, rather than just slipping into abstraction by default. You will use abstraction when these costs get paid for by abstraction's advantages. Is there an abstraction penalty in programming in particular? Some people think so, and measurements, not very recent ones, are the best I have, essentially, when the same language lets you express an idea at a very detailed, concrete level or in more high-level abstract ones, it's a normal, if unfortunate result, that the way you want to use, the way you want to use to maximize your productivity as a programmer, that is the high abstraction way, ends up producing fat, slow, lazy code. That was first observed by Alex Stepanov, the original architect of the C++ standard template library. And so I'm pointing you to the original source where he published his results, and from there you can research abstraction penalty. The point that I'm making here is that this is a transient artifact of lousy implementations. It's not the abstraction's fault that it can be implemented very badly. The specific abstractions Stepanov had in mind were C++ templates, intricate, big, complicated templates to allow very high productivity programming. That was more than 10 years ago that he made these remarks, and things have been getting better even in the C++ world. In Python, I think I can claim with some pride that the implementation is very high quality we do not suffer from an abstraction penalty. If anything, we enjoy an abstraction bonus. For example, suppose you just want to do something for the times. If something here is just a pass, so it's nothing, but I'm assuming you're all slightly familiar with Python. For means a loop, and pass means do nothing here, it's just a placeholder, no operations. The traditional way of doing it is for x in range or for x in x range, and then a loop on a machine that actually, when I measured this, I was using a pretty old and obsolete machine, but anyway, 4 or 5 microseconds. When you use itertools, you use the abstraction implemented in the itertools module of the Python standard library, and you just do the itertools repeat, which is a higher abstraction way to describe do something repeatedly than a for loop. Then the 4 or 5 microsecond become 3. So you're slicing, you're enjoying an abstraction bonus by operating at a more abstract level. You're working substantially faster. Your code is working substantially faster. itertools is a great example, but there are many others throughout Python. For example, what my wife Anna nicknamed the Marshall smiley, which is the construct open bracket, colon, colon, -1, close bracket. That means index, or slice to be more precise, from the beginning to the end with a stride of -1, meaning reversed. So, if you actually detailedly, concretely say, take a string such as abracadabra and reverse it and join it back again, you can take easily with a sufficiently old and unsophisticated machine 6 microseconds per time you're reversing this. If you use the more abstract slicing with negative index, the Martian smiley, it ends up taking an order of magnitude less time. It just flies. That's because you're reasoning at the correct abstraction level. And in Python, you can expect to enjoy an abstraction bonus. So don't worry about the abstraction penalty which old, bad C++ implementations may have imposed on you. You're not going to suffer that if you choose to program in Python. Now, to the core thesis, which I already anticipated, all abstractions leak. So, Mr. Spolsky states it and exemplifies it pretty well. I don't think he explains it. My attempt at explanation is as follows. All abstractions leak because all abstractions lie. As one of the great engineers of the 20th century said, the map is not the territory. Korzybski, the founder of general semantics, was an engineer, and it shows. The philosophers of the 20th century who really delved into the nature of reality and perception are all engineers, like Wittgenstein, Korzybski. That's what engineers do. Before you can abstract, you must really get, I keep using the verb grok, coined by yet another engineer, Robert Heinlein, best known as an author of science fiction books, but engineer to the core. Before you can step back, you must be close. I'm not sure the guy I'm quoting here was an engineer, because this quote is from the Book of Five Rings. And if you're familiar with Aikido, and in particular the Book of Five Rings, even if you will never hold a wooden sword in your hand, I still recommend at least reading the book. But the point is, what he says, like in so many of those ancient Asian books, is concretely applicable to the problem at hand, which is winning a sword duel. Before you can step back, you must have gotten close to your adversary. But he's also speaking a bigger, larger truth in somewhat metaphorical terms. I could say somewhat abstracted terms. Before you can step back from a problem, from a situation, to get the grand view, where does it fit in the whole system, in the whole issue, in all that this corporation, this team, who personally are trying to accomplish. Before you can do that, you must understand that specific concrete thing very well. Before you can step back, you must be close. So, the solution is simple. Abstract only when you know all the details. That, of course, that's impossible. There's more details that there are incidents in your life. If you keep digging down the tower of abstraction, you'll never reach an end, so you'll never get anything done. So therefore, let this impossibility remind us all to be humble. That is, keep your abstractions humble and flexible. Maybe you can see where I'm leading with this, because well, let's give a concrete example. It's easier to understand this abstract discussion of abstractions with one design which I personally believe to be one of the greatest examples of abstraction designed in the 20th century. The TCP/IP stack for networking. Physical network gets abstracted into a data link layer, gets abstracted into a network layer, gets abstracted into a transport layer, and then you have the application layer on top. And the concrete consequences of this abstraction is that every lower layer adds some data, metadata if you want, regarding its own needs to the payload of the higher abstraction layers. So the application layer only cares about the data. The transport layer needs a TCP header or a UDP header or a few other minor protocols. And the network layer takes this thing as a payload and adds the IP header. And of course, the data link layer will typically have frame headers and trailers. That depends on the concrete network. But the point is that as the abstraction gets slowly undone, that is, as we go down from application all the way down to the physical network, the actual packet of data only grows at one or both ends because it gets decorated. So where is the leak in this masterpiece of abstraction? Well, I'm going to focus on only one because I think it's by far the most important. TCP leaks trust. It was designed in an era of trust. There was no hypothesis that people would, or nodes on the net would try to pass themselves off as somebody else. The vast majority of issues that have arisen with TCP/IP over the last 30 years as it essentially conquered the world were all attacks against it. In this case, we're mostly talking about deliberate attacks, although some of these have happened by coincidence, honest, well-meaning error. Attacks from below, address resolution protocol cache poisoning. Attacks from above, domain name system, cache poisoning. Attacks from the side, mendacious border gateway protocol. And from within, the sniffing, the think of the original protocols, application protocols like FTP and Telnet, sending passwords in clear over the net. Isn't that a great example of leaking trust? Hey, I type my password, probably my computer doesn't show me what I'm typing, and then the bits in clear fly over 25 hops to the destination. It's almost sweet, it's so naive from today's viewpoint. This is a survey from a few years ago to IT managers in various corporations. What threats concern you most? And as you see, the vast majority of them are network related and are cases of TCP/IP trust. Why exactly bots and botnets should be considered threats? I imagine it's because of brute force attacks against passwords and captchas or something like that. But if you look at the leftmost line, BGP hacking, Border Gateway Protocol hacking, doesn't seems a worry, but not even such a big one. They're not worrying about ARP caching because ARP happens within a physical area and they can secure that. You can't get to the router physically, or it's reasonably easy for security to guarantee that the router is not something you can just go and hack on. So, but if you could do ARP poisoning. Something you could probably do at the average internet cafe, because I suspect the people around, the owner and so on, have not the slightest clue about what could I do with 5 minutes access to a router, poisoning its cache. So essentially the ARP cache points means that when other people are trying to get to certain nodes on the net, they're going to get to me. I mean, if I feel good, I'm going to forward those packets, but meanwhile I get to look at all of them, no matter what. DNS requires, poisoning DNS requires a bit more parts, but not all that many, depending on the naivete of the DNS implementation, because there's still a level of trust implicit in DNS hookups. That's, I don't want to get too deep into networking. I'm just taking, this is one of my favorite figures. It's what happened to YouTube traffic due to an apparently well-meaning error by a Pakistani ISP. The Pakistani ISP had been ordered by a local court to block YouTube traffic in Pakistan due to some controversy or other about one video or two. How they did it was by poisoning the Border Gateway Protocol caches. Unfortunately, their backbone connection in Hong Kong, I believe, trusted them, accepted their information. And by the way, all this block of IPs, all the IPs where YouTube serves, are mine and go to this black hole, essentially. And that information was spread by the major Hong Kong backbone to all the rest of the backbone on the world, and YouTube got interrupted for hours. I think that was in 2007 or 2008. Only a few hours, but hopefully enough to show at least the major backbone suppliers that you just can't use BGP 1.0 in the 21st century. It was not particularly good even in. Okay, so this is an example of the bad leak, the kind that Joe Spolsky had in mind when he pessimistically said that all abstractions My claim is that there are loose leaks. Consider, for example, something that has kept happening forever, a remote or distributed file system which tries to emulate a local one. The less local the file system actually is, the costlier it is to put an abstraction on top of it. For example, the unreliability of locking operations, mutual exclusion operations on distributed file system is legendary. If you've ever used NFS, for example, was a good example, the semantics are not the same. The reliability is not the same. Sure, your local disk or even a redundant array of inexpensive disks can break, but nowhere as often as something can stumble on the network cable. So, my point is, file system, per se, is a splendid abstraction. Local file system is a horrible abstraction. Which reminds me of a design principle by a colleague of mine, correctly. He was talking about design for Java, but I think it applies much more widely. And very simply put, his principle is never subclass a concrete class. If a class can have specific instances, that is, it's concrete, not an abstract class, then it has no business as having subclasses ever. It's just bad object-oriented design, bad modeling of the world. So don't think, well, I'll have platypus as a subclass of mammal. You're going to really suffer. Mammal, well, okay, if mammal is a concrete class in your taxonomy, because the concrete class has certain implications that a subclass must inevitably evaluate, or else it has no business existing in the first place. A local file system, if you will, is a concrete class. I mean, there are specific examples of local file systems. You can instantiate a local file system to get the file system on this USB key, this file system on this magnetic disk. File system per se, you could see as an abstract class, which instantiate into either local file system or remote/distributed file system. This doesn't mean that to abstract file system is a bad thing. It means you must be able to leak. For example, in the file system case, you should be able, for the remote case, to have a timeout on any operation. Because, hey, I'm trying to read 4 kilobyte. If it can't read 4 kilobyte in 1 second, something is broken. This is a leak in the abstraction, because the abstract file system, you ask it to read up to 4 kilobyte, it will give whatever is in the file up to 4,096 bytes. But you need a way to let the programmer safeguard, okay, what if the delays become impossible, which is probably a symptom that something is broken in between. There is no in between in the abstraction. But there definitely is in a remote file system. There could be half the internet between the file you're trying to read and your machine. Therefore, you need a controlled leaks that, for example, can take also timeouts or callbacks. Like, okay, I'm going to wait whatever it takes, but not like blocking the whole thread here until finally this synchronous operation is terminated. Just call back into this function once the data is finally arrived. That's a different example, but perfectly good too. I wish I could more generally give you principles of how to design abstractions correctly. But I really can't. However, I'm very good at giving you excellent examples of how to design abstractions wrong. Maybe by avoiding the, hey, I don't really have that much experience myself in designing perfect abstraction systems. I do have plenty of experience in designing ones that, in retrospect, aren't really that good. So I analyze my mistakes, and maybe you can learn from my mistakes as well. An example. If you have an interface, if you're designing an interface based on a single class that implements that interface, it's almost impossible to get it right. Because you cannot generalize from a single example. It's hardly possible to say what is concrete to that implementation and what is in common to all sensible implementations of that abstraction. The map is not the territory. You can't abstract the map by having a one-on-one mapping with the territory. Jorge Luis Borges had a great short story about a country where the cartographers took over and fighting the map is not the territory, covered the whole country with a map. Unfortunately, that stopped the sun from getting to the crops, and all the crops, crops failed, and everybody stops. But anyway, as I already mentioned, Haar's principle, subclassing concrete classes, that is, a concrete class is a complete implementation of something, and it can never be the right base for subclassing. You should pull out to an abstract class or interface what's in common to all possible implementations and have them subclass that, not each other. Another example of bad abstraction mid-scale is the errors in encapsulation. Has any of you ever had the misfortune of working with NFC for something? I can feel your pain. I work with that too. Essentially, they had the Windows concept encapsulate the toolbar concept. So if you had no leaks. It was giving you no leaks, no hooks, no way to tell the window. I believe they fixed that in the following version. To tell you, use my factory to make toolbars. So you could use a more advanced toolbar instead of the default one. At the most macro level, we find a very large-scale example of exactly the same problem at the most refined level with which we started this slide. It's the framework, which only has one application. Again, if you only have one application, you have no business abstracting a framework out of it. The framework, on a very large scale, just like the interface on a very small scale, must abstract what's in common to several cases. You can't generalize from a single example, whether the single example is 1,000,000 lines of code in a large application or 100 in a class. Okay, I lied. I do know some things about abstracting well, not from myself, but from other, from studying the reflections. To design an excellent abstraction, you need to master at least the layer below, possibly code. If you really want to design a great abstraction, you must be intimately familiar with several possible ways that abstraction could be implemented. That's what the level below means, right? So TCP/IP couldn't possibly have been anywhere as good as it has been as a design abstraction, were it not for the fact that the young engineers that produced it had worked with several concrete implementations of networking and had this idea of how to implement it in several possible ways. If the abstraction is to be really good, you also need to have similar familiarity with the level above. Otherwise, you can make something that's a great abstraction of possible implementation, but essentially unusable for the application programmer, presumably, that is going to work on top. I mean, seriously, would you like to write a program on top of interfaces, APIs, and so on, designed by somebody who had never written applications? I don't think so. They may be great at, say, file system internals, so they design a file system abstraction, but if they've never written application programs using file systems, it's very unlikely that that file system is going to be easy to program on. You can't afford to wear blinders and look only at what you're designing. You must have a view below, you must have a view above. There are no shortcuts. Remember, applying the golden rule, that is, don't do unto others what you wouldn't want others to do unto you, should be particularly easy in this case, because there's a very good chance that you will be the poor fellow that is the next one who needs to use the abstractions you're designing now. So if you design something that's essentially unusable for the application programmer, it may well be that your karma will come on you, not in this lifetime, but this very one. Your next assignment is to program on top of the sleep in the bed that you've made, say. And similarly, somebody's going to implement your new shiny abstraction, and it could very well be you. If you've designed something that doesn't reflect the reality of the implementation layers, and so it's really hellish to implement, you might be the one suffering through the next implementation. There is occasional justice in the world. Not always, but often enough that these two possibilities should really motivate you to put your best effort. The C2.com site, although most of the discussions are very dated, has a lot, still has a lot of things to teach. So this is one point you can start if you want to follow. What all was I condensing into this single slide? Can you program at this level while still fully aware and conscious of the higher level of abstraction above, the application program to use your interface, your APIs, and the one below, the implementation that will produce your APIs? Well, Donald Knuth says you can. This is from Donald Knuth's interview several years ago in the Dr. Dobbs journal, dbj.com. I hope the URL still works. And this is a literal quote for it. The psychological profile of a programmer is the ability to shift the level of abstractions from low level to high level, to see something in the small and to see something in the large. This is what it means to be a programmer, to have the ability to see things simultaneously at the low level and the high level of abstraction. I'm sorry he says computer scientists. I think he means developer. I always agreed with Dijkstra that computer science is not about computers, just like astronomy is not about telescopes. And this is the famous Knuth quote. I don't know if you're familiar with this comic. It's called XKCD. If you're not, do yourself a favor, do a web search for it, be prepared to spend the next few hours laughing and grimacing and so on. And here the quote from Donald Knuth is, "Who are you? How did you get in my house?" What? That's what he said when I asked him about it. Of course, you're not supposed to get into Professor Knuth's house to ask. Okay. not only you can, as Knuth says, but you must. As Jason Fried said, I already mentioned him as the real expert of user experience. He's talking about copying, but it applies just as well to using abstraction blind. Copying skips understanding. Understanding is how you grow. You have to understand why something works, why something is how it is. When you copy, you miss something. You just repurpose the last layer instead of understanding the layers underneath. The layers underneath are the ones for on which the abstraction is built, from my viewpoint. He's not talking about abstraction, but it might as well be, from my viewpoint. As Jeff Atwood, the partner of Joel Spolsky in founding Stack Overflow, said, don't reinvent the wheel unless you plan on learning more about it. This is the problem. The kid is obviously reinvented the wheel, but I'm sure the issue must have told him a lot about, oh, so that's why they're around. Which could help. Codinghorror.com has a lot more about it, so it used to be Jeff's. Now let me give a good example of an abstraction evolving, which finally does involve a Moodle technology. You may be surprised that I do know a little bit. Abstraction at the beginning was meant to be used to essentially make or drive web pages via handlers, okay? Inside, the handlers used services which all went through an RPC layer, but that was an implementation agent. The abstraction had nothing to do with RPC. So the abstraction did not expose this crucial point. So, suppose you want to exploit the fact that even though the abstraction, the original abstraction, was hiding it, every single use of a service is going through an RPC call. Therefore, you should be able to inject some of your own. For example, let me log all the database operations, or the operations regarding storage, or I want to check to log how much time I'm spending in using the image processing service, and so on. They all go through RPC. So, given that all the RPC layer always goes through make sync call in the API proxy stub map, the first thing programmer that isn't really familiar with the maintenance of abstraction might be to monkey patch it. That is, take advantage of Python's dynamic nature to substitute their own fake function in place of the make sync call function. The problem, if this is not going to work, for example, this is one of many examples. This is a memcache client object that other services expose just the same kind of issues to you. The various functions to use, for example, to initialize a memcache client, are expressed as default values for the arguments. The default values are computed when essentially the class statement executes, which means when the module is loaded. So by the time you get around to patching the makesync call, the memcache client, for example, has probably already gotten the real one and will completely bypass your attempt. As you see, it's using the real lexical. This Jens Scheffler explained how to re-architect App Engine to make specific hooks, essentially make the App Engine abstraction lead in a controlled, designed way by offering hooks in a programmatic, documented, supported way. If you want to do something before every RPC call, you essentially just need to get it on the list of pre-hooks for that call. And then, of course, there's a post hook if what you want to do is to get control after an RPC call is completed. This has allowed, for example, frameworks for testing of engine apps, which essentially set hooks to all the RPC service, all the services, because all the services are provided by RPC, and substitute the actual RPC with a simulation that you can control to make your unit testing fly without actually needing to perform the various RPC operations. If your API, the abstraction you're designing, doesn't have a natural place to put hook, RPC is perfect. It's the funnel which you can obviously, most obviously, where you can have pre-hooks and post-hooks. So in the sense, App Engine is too good an example because it has this RPC choke point, so to speak. Well, you can use semantical ones. For example, if your system does SQL queries, there's one point where the SQL query is actually sent to the database, and one point where the database starts returning results. For example, a cursor with results in it. So that's obviously a key semantic point of any system that has to do with database queries. So the pre-hooks will be able to look at this SQL, modify it if needed, so on, and similarly the post-hooks will do the result. Another excellent way to allow, let's say, post-it-like hooks that can be most easily put on and took off away and put on away somewhere else, is by the event callback mechanism. If you're familiar with Qt, which is mostly thought of as a user interface, library is actually much more than that. It's got the signal slot concept, which matches this perfectly. It lets Qt libraries and your own extension to then offer hooks very naturally. Template method. This goes back to my presentation on design patterns. The template method and dependency injections are two design patterns that are perfect for providing hook. Dependency injection is often thought of as a testing patterns, but I entirely disagree, and this is an example. Suppose you're writing a scheduler in Python. Essentially, you have a queue of events, you can add events to it, and then you run, and all the events happen as scheduled at this scheduled time. And the natural, concrete way to do it is, okay, I just, my next task is to happen at time when, the time now is time of time, so let me sleep for whatever the difference between the two. That is a concrete implementation, but it's also, oh, by the way, the priority queue is not, or wasn't when I wrote this, but 4 times Python built in. It's just this pretty obvious class on top of heap queue. That just a Python detail in case you don't understand what that some module priority queue is. You want things events in a priority queue because they need to happen in the specified order at the specified time. So the problem is how you test anything using this scheduler, because it's actually going to sleep for 20 seconds, makes your test incredibly slow. You don't want that. How do you integrate it with other event loops, like a graphical user interface or a networking event loops? The problem is that concrete dependency on time sleep and time. So you can, again, go for monkey patching, which you may starting to understand is not one of my favorite approaches, actually I hate it. Or you can use dependency injection, showing that, okay, it will help in test, but it also helps in system integration. This is the monkey patching approach. You essentially fake out the sleep and time function with your own stuff, but don't do it. It's like you might interfere with a lot of stuff. You're communicating through covert channels, not on the interface. Optimization's been great. It's an excuse for lazy design. Don't do that. Do this. Have the class, that's your scheduler, take as argument what functions am I to use to know what time it is. Defaulting to time. What function am I to use to wait for a certain duration of time? Defaulting to time sleep. And then, instead of calling explicitly time and time sleep, you'll call self dot where you've saved those two. And this is exactly how module schedule in the standard Python library works. Pass it. Actually, it doesn't even take a default for time and time sleep. You must specifically pass it just so you know their hooks. Dependence injection is a really handy hook. This is, typically you'll want your time and sleep to be coordinated, so making them modules, making them methods in a class is perfectly fine approach. This is an example where they essentially the delay implied in the sleep completely disappears. Wait for t seconds, sleep for t seconds, just increment the current fake time by t seconds and returns immediately. So this is perfect for testing because it's not actually going to slow you down at all. In Engine, you may have noticed that dependency injection is actually being used. Remember that slide a few days ago? It's the same as here. What pickling protocol to use for memcache serialization, how to pickle, how to unpickle, how to make synchronous call, and so on, are all being dependency injected. That may not be of immediate use to you because you're not going to be testing the memcache client, but you can certainly use it to simulate the memcache client with your own code for whatever you prefer. So dependency injection remains one of my favorite design patterns. And that's it. Question and answer time.